Yes, is always. Now show me how to use them here. Show that was 1, 2. Now this is 3. Show that n choose 1. Let's start it this way. Show that 2n minus 1 is equal to n choose 1 plus n choose 2 plus n choose 3 plus n choose n. Sure. So if you can see very well, it looks like this one can be taken the other side and it will be positive. The secret is anything to do with such questions is about the binomial theorem. And the binomial theorem is of this nature. N0, an, n1, an minus 1, bn, n2, an minus 2, b2, nn, bn. So if b is not appearing in what you are given here, b is not appearing, the only way b can't appear is when it is 1. Because if n choose n is there, it must be multiplied by b power n. So if the b power n is not visible, then it's clear that the b is 1, because 1 power n is what I can't see. Because 1 power n will always be 1. So I can't see it if it's being multiplied by something else. If there was to be a b here, I would just get a b. Where is 1? It's invisible because whenever multiplied by anything, you get that thing. So whenever I have such questions, my eyes are on the binomial theorem. What can't I see? Okay, so far, this is our question. If you look at this part here, one term is missing, n0. n0 is not there because it started from n1. The question is, what is n0? n0 is just n factorial over 0 factorial n minus 0 factorial. This is n factorial over 0 factorial n factorial. But we said 0 factorial is 1. So we're remaining with n factorial over n factorial. This is just 1. N number divided by itself is 1. So you can say the missing number, the missing n to 0 is actually 1. But we can see a 1 this side and it is negative, meaning it should be back the other side. It will go here as a positive number. So now we have what was missing. Okay, and the fact that we can't see A and B on top there in our question. And the other side, when you look, there's 2 power n, meaning that our A and B, A plus B is the one giving us a 2, since they are both under the same power. So the choice of A and B, that will give us a 2, and yet not appear on the other side, is only 1 and 1. So what will happen is, say, oh, okay, so Here, it will be 1 plus 1 to the power n, so that we get n0. Even if I have so much time, why should I write n power n? I mean, why should I write 1 power n? As if I don't know that it will just be 1. So you'd get here, you have 1 plus 1 to the power n is giving us n0, n1, n2, n3, all the way up to nn. But our question, this guy here is not there, but this guy has been solved and it is 1. If we take it the other side, it will be negative, but this is 2. So we have 2 to the power n. Then take this the other side, minus 1. We will get n1, n2, n3, nn as required. When you do this, you mean as required. Done.
So,
Hello.
like, remember how we do identities when you have been given, let's say, like you have been given a plus
A minus n1.
so should I continue?
You need to continue. You haven't asked your question.
Oh, oh, yes, when let's say you have been given an identity to say prove this other side to this other side. Then you just have to, we usually just used to pick one side, then we prove it to the other side. So in this case, it's okay to use both sides to prove an identity when it
Yes.
comes to binomial.
The nature of the
Oh, okay.
identity requires that you do both sides.
Oh, all right. Thank you.
Though we're just doing one side.
Let's also, sir, try the other side. We see.
There's no other side to be tried. Because if you try that other side, then you'll be memorizing because you, okay, just a minute. Because you cannot have this thing from nowhere. So that's the reason why. Look, if they tell you to prove that, I give an example, sine squared x plus cos squared x is equal to 1. You can't start from the right hand side and say 1 is equal to what? For you to move. It will be hard. So the same way you cannot attempt to do such a thing is the same way we cannot get the right hand side to go to the left, because the right hand side is a produce of the left. You understand? Okay, the one who wanted to ask, please ask.
Yes, can you guys repeat a n power something? Where are they going? There.
I've only gotten the word going and lost.
I'm asking. You can get me now?
Yes.
I'm asking there on a n and a n minus 1 and b n 2. All these on the mid parts there.
Yeah.
Where are they going? I'm still lost.
Since we have chosen them to be 1, A has been chosen to be 1, B has been chosen to be 1. The time we have A n minus 1 multiplied by B, we'll be doing 1 n minus 1 multiplied by 1, which will just be 1 multiplied by 1, which is just 1. And then you get your 1 multiplied by n choose 1, you just get n choose 1. That's why you're not seeing the ANs there.
Oh, all right.
Okay. So it is always yes. You're supposed to use 1 plus 1 or 1 minus 1 for such identities. Okay, you need more of it. So look, you know what the examiner does? After teaching you such a thing, then they will say, show that 2n minus 2 is equal to n1 plus n2 plus n3 all the way up to n minus 1. After you have understood this one very, very well, you even memorize it. Then you go in the exam, you find, show that 2n minus 2 is equal to that. Then you say, I've never seen. When actually we have said, whenever you see such a thing, your first thing to do is you get a plus b to the power n, n0, an, n1, an minus 1 b, n2, an minus 2 b2, n3, an minus 3 b3, n minus 1, a b n minus 1, n bn. You have this. So like, oh, you're now comparing this binomial theorem in the question. What can you see in the question, which you can see in the binomial theorem? So far, I can't see A and B on the right-hand side of 2n minus 2. So after the equal sign there, I can only see n1, n2, when actually here I have n1, ab, n2, ab, n3, ab. Those products, where have they gone? It means that the A and B have been chosen in this manner so that they should not appear. At this point, it will make sense if I say that's what I have. It makes a lot of sense. Oh, okay. Okay, because even if I put 1 power n, I know it's just 1. Even if I multiply n1 power n minus 2, what is 1 power n minus 2? Multiplied by 1 squared. I mean, 1 to n power is 1. 1 power 2 is 1. This just gives me 1. I get this one and multiply by n choose 2. Multiplied by 1, even if I have so much time in my hands, why should I do that? I know any n product by 1 is just 1. What one? It will be posted in the group. Or for today, I'll post it because some people they have gone to church. So 1 plus 1, we know it is 2 power n. Then we have n0. We have n1. We have n2. We have n3. We have n minus 1. We have nn. Now go back to the question and look at it again. You notice that this term is not there. This term is not there. But what is nn? This is just n factorial over n factorial multiplied by n minus n factorial. So we have n factorial over n factorial multiplied by 0 factorial. But 0 factorial is 1, so we have n factorial over n factorial. This is just 1. So we have 2n. We solve this, it's also 1. So 1 plus n1, n2, n3, n minus 1 plus 1. 1 plus 1 is 2. So 1 plus 1 is 2. Taking the other side, it will be negative. Done.
So, sir, is it always that you have to put that kabok whenever you are?
I'm just using it to say done. If you want, when you get here, you say, hence proved. Okay, I've changed now. Hence proved.
But take a box is fine, sir.
In some questions, there was like a box. The reason where not choosing 3 minus 1, which can also give us 2 as 1, is it because we're maintaining the first term in the binomial expansion to be 1 every time? No. If you tried, let's try here. If you try, you say 3 minus 1 to the power n. You have n0. What is a? 3 power n plus n1. What is a? 3 n minus 1 multiplied by negative 1. Already, this part now will be made negative. Second, you don't know what 3 power n is, and you can't move it out of this position here. When on the left-hand side, you have 2 power n quite all right. But here you have 3 power n. But if you look at what you have there, here we have 3 power n minus 1. But this coefficient is there standing alone, not multiplying anything. That's the reason why we choose 1 and 1. So that we'll avoid this confusion.
Sir, is it only when we're told to prove that we can move values from the other side of the equal sign, like you did here with these two?
Yes, it's only when the proof comes in that way.
But if we're just solving, we cannot.
No. There will be no need. So nice. After now, it looks like things have normalized. And this expansion will keep on coming back. This expansion here
Sir,
hello.
can I just see the previous board?
Okay. You'll see it. Don't worry, it is coming. Oh, I skipped one page. The board is there. Done? Okay. So this theorem has come back. And we simplified it. Someday we said this theorem, this is just 1. So we can just write, this is just n. So we can just write like that. And then n minus 1 over 2. n minus 1, n minus 2, a n minus 3. It keeps going. Then somebody asks you to show. They say, show that. Let me look for this proof here. Where is it? Okay, here. Show that I'm looking for the proof here so that I confuse. So I don't make a mistake. Okay, show that n choose r is the same as n minus 1, n minus 2, n minus 3, all the way up to n minus r plus 1 over r factorial. Since we know that in the expansion of this binomial theorem here, we have a general term that we put sometimes here when we feel like, where when you reach here would say plus dot 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 plus nr a n minus r br plus nn bn. We have that term there. Now we are saying, since we solved some coefficients and ended here, what could happen if we proceeded up to this far end? You would notice that the next term after 3 would be n minus 1, n minus 2, n minus 3, and because we have a 3 here, down we have a 4 factorial. Since when we had the 1 here, down it was 2. When we had the 2, down it was 3, plus n minus 1, n minus 2, n minus 3, n minus 4. We should have a 5 factorial here. We keep going until we hit n error. So it will be n minus 1, n minus 2. We have a long way to go. But when we reach n minus, okay, minus r minus 1, so that we make the down part r. Since it's always big, since this guy is always bigger by 1. You understand that 4 minus 1 is 3. That's why we have this 3 here. 5 minus 1 is 4. That's why we have this 4 here. So r minus 1, if we put it here, then down we'll have r factorial. But if we solve for this part, if we expand it there, it will look like this. N minus, then there'll be a plus 1. As simple as it is.
So have we proved?
All right. This is NR.
Sir,
Hello.
we have already proved.
Bana metaitene kai.
Ma. Hey.
We are waiting for the explanation, sir. For the
Yeah. The proof is here.
Sir.
Once you see this, then you know it's done. Look, guys, this question, when it comes like this, the assumption is that by the time you're reading it, you already have this expansion somewhere. You're just asked to extend it up to this term. So if you follow the pattern from 1, when we have n minus 1, here there will be 2. Now you can write that one as 2 minus 1. When we have 2 here is 3. You can write 2 as 3 minus 1. When there's 3 here, down there will be 4. You can write the 3 as 4 minus 1. The 4 which is coming from down. So for us to have 4 there, it was 5 minus 1. So if we went on down, if we want to write r as our denominator, then on top here, we must have r minus 1. Just like we have had 5 minus 1, 4 minus 1, 3 minus 1, 2 minus 1. So you can also have r minus 1. But at the time when we'll be subtracting r minus 1, the denominator will be r factorial. But since you're subtracting r minus 1, what happens if you expand the bracket? It will become minus r plus 1. Hence, proved. Yeah. So now look, we have run out of time, so we have to log out and immediately come back. We are here to finish binomial. Now the identities we've done enough. We can now do some application questions. So the next 40 minutes we'll be doing application. So immediately we log out, you log back, so the 40 minutes can start counting. Not that you rest for 40 minutes. You log out, immediately log back so that we can start doing the application questions. We won't end this class until we are done with Binomial. So let's log out, we come back.